Howdy, AP PreCal. It is Miss Kosh. Today I want to work on the part of the curriculum that covers Trig Identities. So this is what my kids are about to start, but I thought I would work through Mr. Passwater's notes. We'll see how many videos this takes me, but ready or not, here we go. I may have already done this last year, so anyway, this is me this year. Okay, you can always search my archives, search my playlists. I've tried to create the playlist to be as usable as possible, or as user-friendly. First of all, we have different identities. You should already know these. And these 6 are the reciprocal identities because they're all showing that one trig function is a reciprocal of another. So sine is 1 over cosecant, cosine is 1 over secant, tangent is 1 over cotangent, cotangent is 1 over tangent, cosecant is 1 over sine, and secant is 1 over cosine. Those are the reciprocal identities. These 2 right here are called the quotient identities because both tangent and cotangent can be written as the quotient of 2 other functions. I'm like, where is my brain? Okay, so tangent is sine over cosine, cotangent is cosine over sine. And so what we want to do is we're going to manipulate these to either rewrite expressions in such a way or to prove that something's true. I love doing proofs with trig identities. I love showing that one side equals the other side, and it's like a puzzle. How do we get there? How do we do it? I think AP PreCal doesn't quite go as heavy in trig identities as I would. So for good news or bad news for you, depending on if you like them or not. But this looks just like what you would see in FRQ4. They'll give you something and they'll tell you to rewrite it as an expression involving something, okay? And so on this one, so what I see, so our goal here is to rewrite this so that it has tangent and no other trig functions. So the first thing, one of the strategies that I might do, by the way, if you want to go look up I have a folder I call Bag of Tricks. And so I just have a whole list of different strategies that you can try. Go find that video. It's worth watching. Okay, so on this one, I'm going to take everybody and write them in terms of sine or cosine. Oh, what am I doing? Cosecant 1 over, that's... Okay, you know what? I really need my reading glasses. Y'all don't get old. Okay, so what happens here is that sine is in the numerator here. Cosine is in the denominator, cosine squared. And then this, I can multiply by the reciprocal. So this is like saying times sine of x. Now I see a sine of x times a sine of x gives me a sine squared x. My write-up is not good here. My work is good, but I like to see one step underneath each step, which is why I create this to look a little different, but that's fine. Okay, sine squared over cosine squared is tangent squared, and we're done. We've written that as an expression involving tangent and nothing else. So the final answer is that this right here simplifies to tangent squared x. Okay, the next one, we're going to rewrite this one using secant and no other trig identities. So what I might do to begin is say that this is cosecant is 1 over sine of x, and tangent is sine of x over cosine of x, and maybe you see it already. The next step is your sines are going to cancel. Sine divided by sine is 1, so this is 1 over cosine of x, which is equal to secant of x. Okay, on a scale of 1 to 10, I would put that at difficulty, I'd put that as a 2. Okay. We can discover several interesting properties. Oh, this is our favorite. The Pythagorean identity. So if you notice, what happens here is in the unit circle, here's how I like to do this. If that's my circle, pretend. Any angle, theta, it's called the unit circle because its radius is 1. The x value, hopefully you already know, is cosine of that angle, and the y value is sine of that angle. So I see this lovely little right triangle, which means I can use Pythagorean theorem and say that sine of theta squared plus cosine of theta squared is equal to 1 squared. Well, we as mathematicians are inherently lazy, efficient, and we are going to, this is too many parentheses to write. 1 squared is just 1, obviously. But what we want to do is we don't want to say, if I wrote this, sine theta squared, what this is saying is it's saying take an angle, square that angle, and then take the sine ratio of that new angle. We don't want to do that. Okay, I can't think of a situation where we need to do that operation. What we will do instead is we want to take sine of a theta value, find that sine, and then square it. But we're too lazy to write the parentheses, so what we will do is we will say sine squared theta like this. So these two notations mean the same thing. Okay, so at our school, we had a teacher who her last couple of years were my first couple of years here. I found out later she was the age of my mom, and she was so sweet, but she called this one, she had a real southern drawl. I can't do it. But she called this one, it was so important, she nicknamed the Pythagorean identity the Big Daddy. And so every year my kids giggle the first day I say that, and then after we start working the problem, they'll be like, oh, but it's the Big Daddy right there. And I'm like, yes, of course. And so the Big Daddy right here is the first of the Pythagorean identities. We can also come along and, Mr. Passwater typed that up. We can come along and take the Big Daddy, sine squared plus cosine squared equals 1, and divide through by cosine squared. So sine squared over cosine squared is equal to tangent squared. Cosine squared divided by cosine squared is 1, and 1 over cosine squared is equal to secant squared. I can also come back, I need space. I can also come back and take the Big Daddy and divide through by sine squared. If I do, now I have 1 plus cotangent squared is equal to cosecant squared theta. So my recommendation for kids, when you get your test or quiz or whatever, or you get to an area where you're needing to do Pythagorean identities, I would write at the top of my paper the Big Daddy. I'd write sine squared plus cosine squared equals 1. Then I would, in my head, divide through by cosine squared, and I'd write this down. And then in my head, I would divide through by sine squared and then write this down. So I would have, this is squared, not a 2 theta. I would have those 3 identities there. In class, I probably then would do this with you guys and say, okay, how do I solve for cotangent squared? I subtract 1. So that is a Pythagorean identity. It's a variation on the theme. Okay, and then I have 1. If I subtract cotangent away, I end up with cosecant squared theta minus cotangent squared theta. Okay, I can do that with the others. So, you know what? Let me get a clean sheet of paper and show you what I'm talking about. Okay, if you want to, we can come up with 9 versions of the Pythagorean theorem. Oh, by the way, it's almost Valentine's Day, and I heard a joke, and I think it's funny, and I'm ridiculous. But you be sine squared, and I'll be cosine squared, and together we make 1. Okay, sorry. They don't pay me enough. I have to try and be funny, anyway, so. Okay, I can solve for sine squared by subtracting cosine squared. I can solve for cosine squared by subtracting sine squared. I made a point today, this does not mean that cosine equals 1 minus sine. Okay, that's wrong. Think about it like this. If I have 4 squared is equal to 5 squared minus 3 squared, is that a true statement? Well, 16, is it equal to 25 minus 9? 25 minus 9. 16 equals 16. Life is good. But does 4 equal 5 minus 3? If so, then I will give you 5 minus $3 million, and you give me $4 million in return. Okay, they're not equal. Just kidding. I mean, they're not equal, but I thought it was funny. Okay, then I would come through, so that this would be Pythagorean identity 1, and then variation 2 and 3. I can come back here, divide everybody by cosine squared. And then I can solve for tangent squared. And then I can solve for 1. Okay, and then I can come back to the sine, the original, the Big Daddy, and divide through by sine squared, which gives me 1 plus cotangent squared equals cosecant squared theta. Then I can do the same thing, solve for each of these variables. I think I'm right. Okay, so I have 9 variations on this Pythagorean identity, but the only one that I have to have memorized is this one. Okay, let's go see what we have to do with this. Okay, so there's the 3 Pythagorean identities, and then we can come up with variations by subtracting. Okay, let's see if we can find another identity. Oh, this is one I'm not always I don't use this one very often, so maybe I should. Okay, basically what they're saying is if this is my x value, and this is in my unit circle, I have a radius of 1, I can do Pythagorean theorem and say, well, they're saying x squared plus h squared equals 1, would imply that h equals 1 minus the square root of 1 minus x squared. Okay, so then in our, we can see that theta equals the inverse of inverse cosine of x, and then sine of the inverse sine of the square root of 1 minus x squared. Okay. So those angles, so this angle would equal that angle. And then we could do it the other way. I don't know how often we use these. Maybe I need to do more AP Classroom. It's important enough to make it onto his worksheet. But, I mean, we can see where they come from. They're Pythagorean identities kind of manipulated. Or not Pythagorean identities, but we use Pythagorean theorem in the unit circle. Let's keep going. Let's see what examples he has. Okay, this is another one that looks like what we will see in FRQ4. And so they're saying tangent of x over cosecant of x. Well, tangent, what different ways to think about this? I could say, well, this is tangent of x times 1 over cosecant of x. Well, 1 over cosecant of x is sine of x, and tangent is sine of x over cosine of x, and this is multiplied by sine of x. What? Oh, okay. So now I'm here, and I see that I've got sine in the numerator and sine in the numerator, so that's sine squared. So from here, I see a sine squared x over cosine, but they're saying write it involving cosine and only cosine. Well, so we just said one of the big daddy, where did it go? Sine squared is equal to 1 minus cosine squared. So we can say 1 minus cosine squared x over cosine x. We can't just cancel, but we could split the fraction, right, as a fraction involving powers of cosine and no other trig functions. Excuse me, I think we're done, because that is a fraction. You would be correct if you said this is 1 over cosine of x, no, minus cosine. But I don't think it meets, I think that when they say fraction, they want this. So there we go. What else could you have done? You could have, from the very beginning, said that the tangent is sine over cosine, and that it's being divided by 1 over sine. So starting and writing everybody in terms of sine or cosine is often a helpful thing to do. And then how do we divide fractions? We keep change flip is what my kids will say. I guess their middle school teachers taught them that. Keep this one, change the sign, and then flip this guy over. And so then it gets us back to here. There you go. Okay. My kids, we're going to work really hard on those identities that I've taught so far, and then we're going to take a quiz, and then we're going to keep going. But I'm going to keep going in this video just because I can. I don't know. So come back to this video later if you need to, or if your teachers are going a little faster through this than I am, then I'm going to just keep going for you. Okay, so the next thing are the sum and difference identities, which we can use to create the double angle identities. I have videos on that, so go search my double angle identities, and I think that'll be helpful to see how they connect. Here's what I remember for sine. I like to say it's the sine of, this is alpha plus or minus beta, is equal to the little thing. The sum and difference for sine is sine, cosine, cosine, sine with the same SIGN. Okay, so if it's a plus here, it's a plus there. So sine, cosine, cosine, sine, and I do alpha, beta, alpha, beta. It's not the only way to think through it, but this is how I think through it. Sine, cosine, cosine, sine with the same SIGN. And then, do you see why I'm spelling it? Because SINE and SIGN are said the same way, but they don't mean the same thing. The other one is cosine of alpha plus or minus beta is cosine, cosine, sine, sine with the opposite SIGN. So if it's a plus here, it's a minus there. If it's a minus here, it's a plus there. So sine, cosine, cosine, sine with the same SIGN. Cosine is cosine, cosine, sine, sine with the opposite SIGN. And for whatever reason, they don't make y'all learn tangent, but my IB kids do, so there's that. The double angle identity is, if I came through here, I just can't walk away from, if I use this formula and I'm saying sine of theta plus theta, then it becomes sine of theta cosine theta plus cosine theta sine of theta. Well, that is these two terms are the same. They're in the switched order, but this gives us 2 of sine theta cosine theta. And that's where that identity comes from. The other one, if I come back here, okay, this was theta and theta. If I come over here and say cosine of theta plus theta, then it's cosine theta minus sine theta. So cosine theta is cosine squared theta. Sine theta times sine theta is sine squared theta. And I have this right here straight from the sum and difference identity. Then I can use the big daddy. Where did it go? I can use the big daddy and substitute out. If I substitute cosine squared out, I have 1 minus sine squared. So it's 1 minus sine squared gives me 1 minus 2 sine squareds. Or I could substitute out the sine squared. When I do, let's see. Then it becomes a cosine squared theta minus, in parentheses, 1 minus cosine squared theta. So now I have a negative. Negative is a positive cosine squared. And so there's 1 and another one. That gives me 2 cosine squared thetas and a minus 1. Okay, so there are 3 versions of this identity, and there are different times and situations to use the different ones. So there we go. Okay, let's look at his multiple choice. Which of the following is equivalent? So here's what I see. You could do a, like, let u equal pi over 14, and then I have a 2 sine u cosine u. And so this is the double angle identity, which is equal to sine of 2u. Well, what was u? Pi over 14. So this becomes sine of, I'm showing you every step, 2 times pi over 14, which is pi over 7, sine of pi over 7, and we're done. Okay? The next one, which is the equivalent form of this one, okay, so here's cosine. I see 4 cosine 2x. So I can, notice all of these just have regular x. This is the cosine, so this is cosine of, I could either use cosine squared x minus sine squared x, which gives me 4, not this, because that's a plus. I didn't really cross it off. I could use 4 times, it becomes 2 cosine squared x. Where did my x go? Minus 1. Oh, that looks terrible. I'm so sorry. Which gives me 8 cosine squared x minus 4. 8 cosine squared x minus 4. Yeah, that looks good. The other one that I could have done is 4 times 1 minus 2 sine squared x, which is 4 minus 8. 4 minus 8, but it's, oh, they put cosine there. It should be sine. So that's no good for that. And then this is the double angle. This is equal to 4, this is 4 times 2 sine x cosine x, which this part right here is sine of 2x. Okay, so sometimes they like to make you go from here to here. Okay, next one. Here's what I see: cosine, cosine, sine, sine with a minus here. So this comes together. Cosine, cosine, sine, sine is the cosine, and it was these 2 angles with the opposite SIG in. Okay, this is 2 pi over 16, and 1 pi over 16 gives me 3 pi over 16, but it's cosine of 3 pi over 16. Okay, I think I'm almost, am I done? Oh, no, here, I think this is the rest of it. Okay, so let's see, does that look right? Yep, that's 312. The figure shows a circle centered at the origin with an angle. Okay, the coordinates are, oh, okay. So on this one, here, this is 512, so this is 5, this is 12, the hypotenuse is 13. So what I would do with my kids is I would set this up and say, okay, what is sine of theta? What is cosine of theta? And in the past, when we had to do tangent, I'd make them write down tangent of theta, but we don't have to. So sine would be 12 over 13. Cosine would be 5 over 13. And so now they're saying, what's the value of sine of 2 theta? Well, sine of 2 theta equals 2 sine theta cosine theta. Sine of theta we wrote over here. Cosine of theta we wrote over here. Oh, did you catch my mistake before I did? I see it now. This is 5. That was tangent. This is not. There we go. I caught it when I tried to actually work the problem because I knew they had to have the same denominator because they're both over the same hypotenuse. Here's what I see. I see 10 times 12 is 120. 13 squared is 169. And we're done. Okay. The figure shows 2 circles. Alpha and beta, there we go. The terminal angle intersects the circle. Okay, the terminal intersects the coordinates of P. Okay, P is -5 root 11. Q is 2 root 5. Okay, so let me label these little triangles. This is 2, this is root 5. Square this is 4, square this is 5, so this would be the 9, so the square root of that is 3. This one right here is -5 is the x, root 11. 5 squared is 25 plus 11 is, oh, that's convenient, 36. So the square root of that is 6. Okay, so what are they asking us to find? Oh, different things. Okay, so with all of these, I would probably write out, this is alpha. I would tell you what I would say, sine of alpha equals, cosine of alpha equals, have this set up so that I can answer whatever comes next. Sine of alpha is opposite over hypotenuse, so root 11 over 6. Cosine of alpha, -5 over 6. Here's beta. Sine of beta is equal to root 5 over 3. Cosine of, I've taught this same idea but a little differently. You can go look through my older videos. Exact same stuff. Okay, cosine of 2 theta. I have or 2 alpha. That's not theta. I have choices as to which formula I want to use. It doesn't really matter. Let's say that cosine of 2 alpha is equal to 2 cosine squared alpha minus 1, just because I have to pick something. And so this is 2 times cosine of alpha squared minus 1. Well, do we know what cosine of alpha is? Yes, we wrote it down. -5/6. Square that. I have 2 times 25 over 36 minus, that's going to give me a denominator of 18. 18 over 18. So this goes in here 18 times. So 25 minus 18, I see 7 over 18. And I ran out of space, but there you go. Okay, sine of alpha plus beta. So sine is going to be equal to this. The sine sum and difference is sine, cosine, cosine, sine, with the same SIG in. And now I just have to go find those values. Sine of alpha, we wrote down up here. Cosine of beta, we wrote over here. Cosine of alpha, we wrote here. Sine of beta, we wrote here. I was thinking root 5 over 3. So what do? I write a 3. Root 5 over 3. Okay, so I see a denominator of 18. I see this first part is 2 root 11. I see minus 5 root, oh, what was that again? 5. My bad handwriting, I'm sorry. Okay, how about I get another clean sheet of paper for this last one? Here's a blank spot. Okay, cosine of alpha minus beta is equal to cosine, sine, sine, with the opposite SIG in. Okay, so now we can look back at we've got it all written down somewhere. So cosine of alpha, -5/6. Cosine of beta, positive 2/3. Sine of alpha, positive 11, root 11 over 6. Sine of beta, root 5 over 3. And I see a -10 plus root 55 all over 18. And there we go. I think that is the end of his notes. So I have a ton. I'm looking around to see if there's more. I think those are his through 12 notes, which is very fun and very great. Like, subscribe, comment, and you can search my channel for more and more and more Trig Identity stuff. All right, good luck. Go practice.